networks are made of nodes and edges. Nodes are nouns, they're people, places, things, in our case, bats. And the edges are the relationships between those nodes. And most often, node in network theory, the edges are, the strength of those relationships are the width of the edges. So a strong relationship is described with a thicker edge. So how can we do this with bats? So we can look at the roost network. So this roost network is our roosts that are connected by the same bat. So the same bat is visiting these roosts. And then when we add other bats, we can see how those bats are also using those roosts. But while habitat use is innate, it can be influenced by conspecifics. For example, this bat might have wanted to roost in the tree, but this bat was like, hey, let's check out this building instead. And so we can make a social network where we have bats that are roosting together. And how often they are roosting together might indicate the strength of that relationship. So here we have this bat roosted more often with this bat. And so we see a strong relationship, where this bat did not roost as often with that bat. So we see a weaker relationship, and we can see that with the edges. Now bats, they create these fission-fusion dynamics, which means they come together in a big group, and they might break off into small groups. And so we can see here that this is a big maternity colony, they're hanging out together, and then they might split up into other groups, using different habitats. And this could be due to multiple reasons. One could be thermoregulation, to help with offspring development, could be for information. If I'm with a bigger crowd of bats, they might know where there's the best foraging, or if I'm a young bat, they might help me to follow other bats to a higher vernacular. Could also be due to predation. If there's more bats, there's more eyes around to look for predators, but it also might be a big signal for predators to be like, oh, there's food right there, a buffet. And also could influence parasites. More bats could mean more parasites. And so they might want to separate into smaller groups so they can avoid that parasite invasion. So with these networks, what are some questions we can answer? Well, we can figure out the relative importance of these roosts within the network. So we can look at the centrality. So the centrality, there's multiple ways to measure this. One is the number of connections. So that's how many bats are visiting one roost. Another way is not only how many bats are visiting that one roost, but how well connected that roost is to another roost that is well connected. And so we can get an idea of what bats are using the roost most often and how that roost might be connected to another roost that's very important in the network as well. We can also look at modularity, which is the strength of division. So if we have a very tight-knit community, it'll be one big group, be one big community. But if these bats are going off in different locations, it could be due to lack of connectivity across the landscape, and they're roosting in their own locations. We'll see separate groups. So this is all very important for our three imperiled species, the little brown bat, the one-ear bat, and the tricolored bat. And the tricolored bat is one bat we have very little information on. We had 2 maternity roosts until recently, where we found our third one. And I'm using that maternity roost to answer questions such as characteristics of roosts across the landscape, the roost network, and the social network. So what we do, we went back to our maternity site that we did last year. We caught bats using a hoop trap. It's just basically a hula hoop with a net on it. And then we also used mist nets. The bats that we tagged 13 in 2023, and we tagged 36 in 2024. And we used our low-tech MODIS tags. And then we used a handheld receiver to track them to trees and to buildings. And then we also collected information at the landscape level. So first off, I'm going to start out with the tree roots. So in 2023, we found them in 4 tree roots, and in 2024, we did an amazing job and found them in 27. We collected information on the genus of the tree, the DBH, the crown position, and the crown position is just the relative position in the forest stand. So we have co-dominant trees, you can see here with the C, they're getting sunlight at the top. Our dominant trees are getting sunlight at the top and on the sides. Our intermediate intermediate trees, they're getting a little bit of sunlight, and then our suppressed trees, those are typically yearlings, and they're not getting very much sunlight. We also looked at the decay stage, where it goes from 1, alive and doing well, 2, declining, 3, dead, and then it just keeps getting more and more dead. Okay. For 2023 and 2024, we looked at availability, and we did that 2 different ways, and so we decided to analyze the data separately. So in 2023, we focused on the 5 nearest trees, and in 2024, we did an 11.4 meter buffer around the roost tree and counted those as available trees with a cutoff of 10 dBH, or 10 centimeter dBH. So what did we find? So this is all our data combined for 2023 and 2024. They liked decay stages that were healthy and slightly declining. We did find 1 bat and 1 snag, and they really liked maple trees. But they also roosted in a lot of variety of other trees. And while they did like maple trees, and they did roost in a lot, this was our most common tree. So using a Bayesian model, we found out this was not a non-significant predictor of roost selection. They're just roosting in a variety of different trees. For our crown position, they were mostly roosting in co-dominant trees, so the ones that were just getting sunlight at the top. A few dominant trees, and some intermediate trees. We never found them in suppressed trees. According to our model, this was also a non-significant predictor of roost use. Now looking at DBH. So the smallest tree we found them in was 13.25 centimeters, and the largest was 104.14 centimeters. Now we did find that they roosted in larger trees typically. So on our y-axis, this is our DBH, and then for each one of these is our roost. And this is only for 2024, but we can see what the available, which is our box and whiskers in the blue. That's all of our available trees for that roost. And then our little red is our roost tree. So these are the available, and then the red diamond is our roost tree. And we see a lot of the times they're picking the larger tree in that area. And when we plotted this, we found out, yes, DBH, as it increased, probability of roost use increased, but the relationship is very weak. It's not a very great predictor of roost site selection. Going on to our buildings. So since we did the same process with availability for 2023 and 2024, we combined these. We found them in 5 buildings. We collected information on the roof type, the material, the complexity, which just indicates how many hiding holes this place might have. If it's a shed, it won't have that much compared to a very complex house. We also collected information on height and area. And what did we find? We found out they like to roost in all different types of buildings. They'll roost in tin, ones with tin roofs, asphalt roofs. They'll use conventional wood, even masonry. And the complexity is just a variety. This picture is taken from a shed that is so close I can reach up and grab the bats. And so, according to our Bayesian model, none of these were significant predictors of roost use. Now, when it comes to significance, we get more information at the landscape level. So, at each one of the locations, we did an 80-meter buffer and collected information of the land cover. And what we can see with the percent, they're more often in broadleaf forest compared to the available. The available is in this pinkish color, and there's lower in mixed forest compared to the available, and especially cropland. We also collected information the roost distance to nearest body of water. With our percent land cover, since it's so correlated with one another, we ran a principal components analysis. And for our first principal components analysis, as we can see here, this was a significant predictor of roost selection. It's a gradient of cropland to mixed forest. So as we increase in cropland, we actually see a decrease in probability of roost use. And as we increase in mixed forest, we see that the roost use probability increase. Now for our PC2, that was a strong relationship. We see that on one side of the gradient, it's mixed forest and cropland, and on the other side of the gradient, it's broadleaf. And so as we increase in probability of roost use, we see an increase in broadleaf forest. Near bodies of water, as we get further away from the body of water, decrease in probability of roost use. However, this is also a significant but weak relationship. So now to our roost network. So this is roost data from 2024, since that's where most of our data was from. And in the center here, that's our maternity site. And the rest, that's our trees, mostly all trees, and then we found them in one building in 2024. 20 set of trees and one building. Now we use centrality to get an idea of what is an important roost in this network. And in the center here, that is our maternity roost. That is where all of the roosts are connected. Every bat is connected to this maternity roost. There are some other roosts on the outer side that do have a lot of connections as well, but the maternity roost is serving as a spatial anchor when it comes to the roost network. So most of the connections, and it is the shortest path from one roost to another. So this is our social network. It's also the flying spaghetti monster. And what we can see here is all these are bats. These are bats, and the edges indicate how often they roosted in the same place together. The thicker the edge and the darker means the more significant, or the stronger the relationship. And what we found is that bats roosted either 1.98 times together, the smallest was 9 or 1 time together, and the largest amount of roost times together was 13. And this is significant. So we're finding that bats have preferences for which individual that they're hanging out with. But our modularity, which is like separating these into groups, is very low. Modularity goes from 0 to 1, and we're finding that it's 0.06. So while they have a preference for roost mates, they're still a very tightly knit group. And so we're seeing this fission-fusion dynamics. We're seeing that they're going to the maternity site. So if we look at our nodes, they're colored for how many bats are at the maternity site. Those associations are happening primarily at the maternity site. So bats that are wanting to hang out with each other, they're most often at the maternity site. So we're seeing bats coming and going from the maternity site and forming these smaller and larger groups. And so while the maternity site is serving as a spatial anchor, it's also serving as a social anchor. So, roost use. Tricoloured bats, they're not picky. They like to roost in a lot of different things. This is a paper birch tree that Leah found them in. This is the shed. This is the maternity site. It's in a barn. While bats roosted in trees with higher DBH, this is still not a very strong relationship. At the landscape level, that's where we see more of the significance. Bats were selecting for roost more broadly forests over croplands. This could be that pesticide use. There's probably not a lot of foraging sites. It's open, could be exposure to predators, and obviously there's less roost. There's not a lot of trees on croplands. And the roost network, we're finding the maternity roost is critical location for this colony. Individuals are constantly using it. They're coming and going from the maternity site, and this could be because it serves as a place for information. Bats can go there and find out where's the best foraging sites, especially because they're insectivorous, and their foraging sites might move a lot. And so this gives them an idea of where to go. It also might help serve for young year to find out where the swarming or hibernacula sites are. Our maternity site served as a social anchor, so we're seeing this connection between sociality and roost network. And so we should conserve a larger landscape to allow for these complex social dynamics, to allow for fission fusion. And we have to protect this connectivity across the landscape so they're able to come back to the maternity site or be able to go away from the maternity site, seeing what they need. So for my final, bats should be managed at the scale of the roost networks, with the maternity roost serving as the central node. So focusing on the maternity site, but also making sure that you're saving across the landscape for all these other roost networks that are just as important. And with that, I'd like to thank all the people that helped me out with this project. I couldn't have done it without them.
Thank you, Erin. We'll time for 2 questions, and then we can quick
Are those with stronger connections more similar to if they modulated each other or not?
Second, sorry.
Are adults that have stronger connections, more genetically related to each other?
So that is, we're trying to figure that out. We did collect genetic information. So there are two bats that did roost constantly together, and I have a feeling that they're twins, because basically, they were twins, and they were just, the numbers of their tags were really close, which means that they were trapped pretty close in proximity together, and so I have a feeling that those are twins that are constantly roosting, but we don't have the genetic information yet. We're still trying to get that going.
At the landscape level, you said you use a daily buffer. How did you determine that?
I determined that from a previous study done down in Kentucky. I want to say it was Cable and Wilcox. They were looking at the roost network and found how far away the roosts were from each other, and I used that as my buffer.
Super. I think we gotta get moving. Sorry, James. Thank you, Erin.
While Brad is getting our IT set up, if your phone is missing its human, please come see me.